All right, this lesson we're looking at traveling, which is moving around on a graph or a network. So depending on how you're moving around on a graph, we can identify your movement as all different types of things. And here's a nice flowchart that you can follow when it comes to identifying what kind of movement that you're doing on a graph. So first thing you need to decide is whether your movement or your travel starts and ends at the same place, same vertex. If the answer is no, then it can either be, well, it's going to be a walk either way, whether the start and ending part is the same or not. So any sort of movement that you want to do on a graph is a walk. Now, if it doesn't end on the same place, and in your movement, if there was no edges that were repeated, it's a trail. But if it's a trail, you can have vertices that's repeated, as long as no edges were repeated. But if you had no repeated anything, edges or vertices, we call that a path. Now, on a closed walk, so if it started and ended at the same place, and you had no repeated edges, it's a circuit. If you had no repeated edges or vertices, it's a cycle. And then we're going to move down to different types of trails and circuits. So if we have a trail, meaning there's no repeated edges, but we end up following all of the edges in a graph, we can call it an Eulerian trail. And if we have a circuit, so no repeated edges and ends at the same point, and if it follows every edge in a graph, then we call it an Eulerian circuit. Now, that is a fair amount of trial and error that you'll have to do to determine whether any sort of graph has an Eulerian trail or a circuit. So luckily, here are some ways that we can tick off before trying out if a graph has one of these. So here are some conditions. It needs to be a connected graph, has to have exactly 0 or 2 vertices with an odd degree. If there are no odd vertices, the Eulerian trail can start anywhere. If there are 2 odd vertices, the Eulerian trail will start at one of the odd vertices and finish at the other. So let's look at this graph over here and see if it meets all these criteria, and if it does, then let's find an Eulerian trail. So it is a connected graph, that's good, and we want to know how many degrees each vertices have. So this one obviously has 1, 2, 3. This one has 2, 2, 2, and 3. And if we just highlight which ones are the odd vertices, it's these two. So we have exactly 2 vertices. So this one's also good. And because we have 2 odd vertices, we'll skip the 3rd dot point. We'll go to the 4th one. If there are 2 odd vertices, the Eulerian trail would start at one of the odd vertices and finish at the other. So meaning if it starts here, it needs to finish here. Or the other way around, start here and finish here. So let's see if we can find one. So we just need to start here and have no repeated edges. So if we go this way, let me make this a bit thicker so it's easier for you to see. So if we go this way, and then we go, which way? This way, this way, this way, this way, and then this way. So that way we can have one. And if we were to write it down, it will be, we went E to A D, E, B, C, and back and then D. In an Eulerian circuit, the conditions are a bit easier to find as long as it's connected and has all vertices that have an even degree, and then that means that can be an Eulerian circuit. And then we're moving on to special types of path and cycles, Hamiltonian paths and cycles. So similar to the Eulerian trails and circuits, this has to do with vertices. And sorry, I meant Hamiltonian path and cycles is to do with vertices. Oop, wrong pen. To with vertices, whereas the Eulerian circuit and trail are to do with edges. So here we're focusing more on vertices. So a Hamiltonian path is a path, so no repeated edges or vertices, that visits every vertex, so it goes everywhere. And Hamiltonian cycle is an Hamiltonian path, so same as this one, but starts and ends at the same vertex. So some conditions for Hamiltonian cycle. Again, it needs to be connected. Has to have degrees no less than 2 for every vertex. So they all have to have at least 2 edges connected to them. And then something called cut vertex. We don't want any if we want a Hamiltonian cycle. So a cut vertex is a vertex, if we were to remove it, makes the graph disconnected. So it's connecting sort of 2 graphs together, so we have one connected graph. So an example is this one here. This vertex is a cut vertex. Imagine if that isn't there, these, or if it was one here and one here instead, these are virtually 2 separate graphs, and because of this one cut vertex C, now it's just one connected graph. So because of that, we know this has no Hamiltonian cycle. However, it might have a Hamiltonian path. And this is a bit of a trial and error process. So as long as we don't repeat any edges or vertices and move around the vertex move around the graph, then we can find one. So we'll start here, go here, 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 and here. So if we go that way, we are not repeating any edges, not repeating any vertices, but visiting every vertex. So that's a Hamiltonian path. And for this graph B, if we can carefully see if there's a Hamiltonian path here, this way, this way, this way, and then this way. So you can see there's a Hamiltonian path right here. And then for a Hamiltonian cycle, let's check if it's connected. It is. No vertex with less than 2 degrees. That is also true. And there's no cut vertex for this one. So if we're careful, we can find one. So this one looks like a good place to start because it has a lot of edges going from it. So if we go this way, this way, this way, and then this way, and come back to A, you can see there's a Hamiltonian cycle right there.